Thank you. Okay, seems you can hear me. So I'm Björn Gustavsson. I work at the OTP team at Ericsson. I worked there for 28 years. About that, Bogdan/Björn. Bogdan started Event Beam. I continue to develop and make it better. So that's the reason. Yeah. So this is not what I'm going to talk about today. I'm going to talk about code coverage. And first, to make some things clear about my title, it could be interpreted in different ways. So a little bit explanation about that. This is about code coverage covering Erlang code, to see how much it's been executed in Erlang code. And the native refers to its native code in the just-in-time compiler, the JIT. So that's why it's native in front. So and code coverage is useful. You can see if you not have enough test cases, it can be useful for that. It can also help you find deficiencies in your code. So I'll show an example for that. So we jumping into an example. This is a Fibonacci sequence, and each number is the sum of the two preceding numbers. And we can implement in Erlang easily, like this. And then we can collect coverage on that. So we'll first need to cover compile it to prepare collecting coverage information. Then we can run it as usual, calculating for Fibonacci number 19, get the result. Then we can do an analyze, and with this option it will generate an HTML file, which we can look at in a web browser, like so. So there are all lines are covered, they are green. So that is good. At least we have covered all lines. There also count number of times each line was executed here in this column. It's kind of high numbers, so it's probably not a very efficient implementation. And we can verify that. We can time the execution. And the first number is the number of microseconds for the execution. And it's about 1.5 minutes, so it's not very efficient. And then before we start to try to do it faster, could there be any other problems with this code? For example, if you try calling with a float, what will happen? It turns out that it will not terminate or not in any reasonable time anyway. So I have to abort this. So this code was fully covered, but that doesn't guarantee that there are no more bugs anyway. So here is a better version. It's faster, and the guard test only allow integers greater than 2. So we can run coverage on that as well. I mean, if you now look at the column of executed counts, it looks much better, much more reasonable. And you see, we have uncovered lines. They are red, and they also have sad faces. and there's a reason for that. You can search for the sad faces in the browser to easily find all uncovered lines. I use that all the time. I actually requested for the maintainer of the cover tool to make it easier to search. It used to be a 0. And we are very particular about coverage for the compile application. We want to have as much coverage as possible. So I'll look at uncovered lines a lot and try to cover them. So now I'm going to turn to how cover is implemented, and I will return to this simple example. So cover has been around for a long time. Before OTP 22, we used as update count. Yeah, well, okay, I should say that cover will insert extra code to count when each line is executed. So here's how it was done before OTP 22. We used ETS update counter, inserted that code on each line, and then when you're doing that analyze step, it will read out the counts from that table. That was improved in OTP 22 to instead use the counters module and keeping the reference to the counters array in persistent term. And that was a little bit faster. And now in OTP 27, we built support into the runtime system, the JIT, to do this counting, to further reduce overhead. So there is a new instruction called executable line. And this is pseudocode. This is not real Erlang code. It's just how it's printed. So we'll have to dig a little bit deeper into the beam. So here we have only the first clause on line 4. And now we'll see how does this look in beam code. So here we have that. So there is an executable line instruction inserted before the code that returns the 0. And dropping down further to the JIT code, the native code, so two instructions to increment to counter here. So now I run the standard lib test suite in different ways. First without any covers, and then with cover in OTP 27, the default one, and you see, yeah, it's slower, but not 12%. And I also compared to the old implementation, I forced cover to use the counters module, so it's still a bit slower, 35% approximately slower. So next, I'm going to talk about this new functionality in runtime system for recoveries that can be used directly using BIFs and options for starting a runtime system. What we don't have currently, we can't generate web pages like this with annotated source code. So if you want that using the native function directly, you will have to do it yourself. But so there are BIFs to read out info. So we'll look at that. So if you only want to find out which functions are executed all, this option can be used, JP cover function. We tell we want on a function level. And there's no need to prepare any beam code. The beam loader will instrument the code, insert extra instructions by itself. There's no need to prepare the beam files in any way in doing this. And when we start a runtime system, we can read out coverage information for any module using this BIF code column get coverage. So there is a level that can be function or line, and then we give the module name. So here I show it for the init module. This is the very first module that it executes when the system starts up, and it's obviously not possible to use the cover tool to find it coverage for that, because the cover tool is not running. Yeah, but here we can see. Here we see all functions in the init module, truncated to fit on the slide, obviously. And there is a boolean where true or false for each function. And using that, we can count the number of cover lines and uncover lines in the input, like so. If you want more information, if you want to know times each function was executed, we use the function counters mode. We do the same call to read it out, but now we'll have counters for each function instead. If you sort this, we can produce a top 10 list of the most executed functions starting up. So next, let's see. We look at how this is implemented in native code. So a function covers it just writes a value to an array of Boolean values, and that is very fast. It's almost free doing that. We look at some numbers about that in the next slide. And to increment, if your function counters mode, it needs to automatically increment the counter. That is a little bit more overhead because there's a lock prefix needed to make atomic to make sure you don't skip values, and that costs. There needs to be synchronization between CPU cores. So okay, so let's see how much that will cost. Yeah, so you see there now I run the compiler as a benchmark. So all code was instrumented. The compiler test suite, the compiler, kernel standard lib modules, everything. So we see here that in the function coverage mode it's 3 seconds slower, or about 1%. But if you want the counters, it's 36 seconds slower or 16%. So that makes a difference. So if you want the least penalty possible, you can run the function coverage mode, which can also be very useful. So let's see, what did I have next here? Yeah, there's also a BIF. Instead of starting the runtime system with an option, there is a BIF to do the same thing to set the mode, and then all code subsequently loaded will be instrumented in that mode. So here you can instrument on the fib module. So you can only instrument the modules you're interesting to further reduce performance penalty. And then I reset it to not do any instrumentation. And if we can call Fibonacci number 19 again, and here we can retrieve the code coverage for a function. See how many times it was called. And then we can also do line coverage. And in this case, the beam files need to be prepared by using this option when compiling the file line coverage option. And we'll need to start the runtime system like this. So both must be done in order for it to be instrumented in runtime. So here we can, when we've done it like this, we can call fib19 again, and we can get coverage. And in this case, we'll get line coverage. So we get in this way. We can't get any web page for this. So here I've shown how these numbers corresponds to the line of our code here. So I think, yeah, it's time to wrap up. Okay. Yeah, so code coverage, it can help us find deficiencies in our code. Execution counts can show that they executed too much or something, so that can be very useful. And if you don't, even if you have full code coverage, it does not guarantee that there are no more bugs. We will need to think a little bit more to see if a line covered, could it be in different states and so on. So so the cover tool is fast in OTP 27 when the JIT is enabled. If you are using 32-bit runtime system, it will run in the old way. So as I showed, the native code coverage function, it can be used directly if you need less performance penalty, or to collect coverage for system modules, for example, the eNet module, or server process, for example, the code server. It's not possible to collect coverage for that either using a cover tool. And perhaps you have custom tools you want to integrate, so it can help with that, can be easier than cover more. So, but we don't generate any web page, we annotate the source code as yet anyway. So I think that was all I had to say. Thank you for listening.
All right, let's find at least a minute or two for questions. I see you raised hand, that's good.
Yeah, thanks. It's more a comment than a question. So the high overhead you have with the counters, and you said you need the locking for the CPU synchronization and so on.
Yeah.
The common way to avoid that is to have per CPU counters and add at the end, right? So you would have.
Yes.
Did you look in that, or do you have this in mind? Because I think it would drastically reduce
We
the
did.
overhead.
Yes, I did think about that, but I thought for the first release, I didn't want to do that. It's more code. Have to keep allocate all the arrays for different stats. So that is a possible improvement, and that is actually the counters module does it in that way. So that it will use more memory. That it does exactly that way. So that could be a reason that the difference between the counters and this one is not that great, because the counters is a little bit smarter in that way.
Okay, do you have additional questions? Yes.
So in the last approach you showed with the line coverage, we could also imagine having just line coverage without the counts here. That could be a middle ground.
There is such a mode also. I didn't show that.
And this will be the final question. No pressure.
So the benchmark you showed in the beginning for the standard library with the new coverage, was that with the line mode you showed in the end, or was it with the new cover tool? And if it wasn't with the new the line mode you showed in the end, do you know what the performance is for that new?
It is the same. The cover tool uses the line coverage mode that are showing in the end, so it should be the same.
Right.
Same. Yes.
Right.
Yes.
Thanks.
All right. Thank you once more for your talk.
Thank you.